So this is lecture 15 on positive definite matrices. Okay, so positive definite matrices are a special type of symmetric matrix that frequently appeared in applied mathematics, like physics and engineering. Okay, so if we start with a matrix A, okay, symmetric, okay, we can associate to every matrix A a quadratic form of this type. Okay, so this is how you write it. It's going to be x transpose times A times x, where x is a vector of variables. Okay, so here x will be x1 and x2. Okay, so you write this expression and you multiply it out, and it gives you a polynomial like this in two variables, and each term has degree 2. Okay, so if you look at this expression and you want to know what matrix generated this expression, it's actually not that hard. Okay, so the term in front of the squares, so x1 squared and x2 squared, those two will just go on the diagonal like this. And the cross product terms, okay, we have a 4 here and a 4 here. We add those up to get the sum here, 8 times x1, x2. Okay, so it might be more apparent when we look at a bigger matrix here. Okay, so if A is this 3 by 3, okay, you can tell it's also symmetric, then its quadratic form is this again. Now x has 3 variables, okay, and then if we multiply this all out, this is what we'll get, a much bigger expression. Okay, but it's actually, again, easy to see the correspondence between this polynomial and the symmetric matrix that generated it. Okay, so again, on the diagonal, we have x1 squared will give 4, x2 squared will give 3, x3 squared will give negative 5. Okay, and then we look at the cross products that are in symmetric positions. Okay, so this and this go together. Okay, and we sum them up, and that will give us x1, x2, or the coefficient of x1, x2. Right, because they're in row 1, column 2, and row 2, column 1, respectively. Okay, so this is sort of the 1, 2 position. They sum together to give the coefficient of this. Similarly, the row 1, column 3 position, or the row 3, column 1 position, we sum those together to get negative 12, x1, x3, and we sum 1 plus 1 to get 2 is the coefficient of x2, x3. Okay, and so that's how you go from this to this, right? Going from this to the matrix, you just do the opposite thing, right? Since I have a 2 here, I'm going to split that in half to the 2, 3 position. Since I have a negative 12 here, I'm going to split that in half to the 2, 1, 3 positions, and so on. Okay, so it's a little hard to describe in words, but if you work out a few of these, you'll get used to it, and you can quite easily go between them. So the important question that comes up in applications corresponding to symmetric matrices is, when is this polynomial always positive? Okay, when is this positive for any x we put into it? Okay, so if I put in the 0 vector, all zeros into this, it will be 0. Okay, but when is it going to be positive for all the other x's we put into it? Okay, so it's not easy to tell just by looking at this, right? It's not even easy. It's not easy to tell looking at the simpler one, right? Okay, so this part will always be positive, right? This part will always be positive, right? But this part could be negative, right? Because we have x1 and x2. So if one of x1 and x2 is negative, then this part will be negative. Okay? The question is this part big enough so that the negativity will exceed the positive parts here? So it's not clear just by looking at this whether this will be true or not, right? So this looks like a question for calculus, right? This isn't a linear equation anymore, right? And we're trying to determine the range of it. So this seems like not a linear algebra problem. But it turns out linear algebra will completely answer this question. Okay? And the answer lies in the eigenvalues of this matrix, the symmetric matrix. Okay, so the condition that gives us positivity is going to be called positive definite. Okay, so a symmetric matrix is called positive definite if all its eigenvalues are positive. So I'm claiming that the answer to this question is when is the quadratic form positive is when the eigenvalues of A are positive. Okay. So remember, A is symmetric, so we know it has real eigenvalues, so it makes sense to say eigenvalues are positive or negative, right? Okay, so in applications in physics and engineering, this term here, x transpose A times x, so this up here, is often called the energy, or the energy of the system. Okay, x might model the position of a particle, and this quadratic form will describe its energy at certain positions. Okay, so that's where the word energy comes from. Okay, so we say a square symmetric matrix A has energy, okay, this term. A is positive definite if the energy is positive for non-zero x. Okay, that is, A is positive definite if the energy is greater than 0 for all non-zero x. Okay, so this definition is the definition corresponding to the question directly. Okay, and the eigenvalue definition is sort of an answer to the question in terms of linear algebra. Okay, so what we have to do is prove that these two definitions are actually the same thing. Okay, that the energy will be positive, with the exception of 0, exactly when the eigenvalues of A are positive. So that's what we have to prove now. Okay, so first we'll prove the forward implication, or the forward direction, right? I'm going to assume that A has positive eigenvalues, okay? And I'm going to conclude that that always implies that the energy of A is positive, okay? So we're going to prove that. So this is sort of a long-looking proof, but it's a good proof because it shows off many of the features and properties of a symmetric matrix we've been talking about. Okay, so let's suppose A is a symmetric matrix, and we'll suppose that A has positive eigenvalues. Okay, so that's where we're starting, and I'll remind you, our goal is to prove that the energy will be positive, right, if we assume positive eigenvalues. Okay, so we suppose A has positive eigenvalues. Okay, that means, you know, if V is an eigenvector, we have this relationship with its eigenvalue. Okay, so let's consider the expression V transpose AV. Okay. In other words, the energy of V. Okay, so I can immediately rewrite this. I know that AV equals lambda V just by the eigenvector equation. Okay, and now I can just put the lambda on the left-hand side. Since it's a scalar, I can move it around. Okay, and so I get lambda times V dot V, right? This implies that, this expression must be greater than 0, right? Why? Because we're assuming that lambda is greater than 0, and V dot V will be greater than 0. Since V is an eigenvector, it's non-zero. Okay, so the energy of an eigenvector, okay, will be greater than 0. Okay, so that's not quite what we want to prove, right? What we want to prove is that any vector in Rn has energy greater than 0. But we've just proven it for the eigenvectors. Okay, so let's remember something about the eigenvectors of A. Okay. Since A is symmetric, it's orthogonally diagonalizable, and so there are orthonormal eigenvectors, V1 through Vn, that are a basis for Rn. Right? It's a property of symmetric matrices. Okay, and so since these V's are a basis, okay, that means for every x in Rn, we can write x as a linear combination of the basis elements, right? Okay. Now, let's consider x transpose AX. Okay, this is what we're trying to prove is positive. Okay. Now, if I just plug in this expression for x into the x's that appear here, I get this, right? And now I'm going to multiply A through this. Okay, so I'll get A times C1 V1, right? But since A times V is equal to lambda times V, right? This becomes C1 lambda V1 just by the eigenvector equation. Okay. Now I'm going to translate the transpose here into a dot product. Okay. And now I have a dot product between these two. Okay. So if I dot, if I expand the dot product like I would distributing multiplication over addition, right, then I'll get a lot of terms, right, but most of them will turn to 0, right? We'll get a lot that's vi dot vj, where I is not equal to j, okay? But since we're assuming or since we know the eigenvectors are orthogonal, each of these dot products will disappear. Okay? So most of the terms in this expansion will disappear. The only ones that will remain will be when I'm dotting vi dot itself. So v1 dot v1 will remain, right? That's this dot this, right? And like vn dot vn will remain. That would be this times this. And in the middle, there'll be c2 squared v2 dot v2, right? Okay, so I have this expression remaining, and I know the following. I know lambda is going to be greater than 0. By assumption, we're assuming all the eigenvalues are positive. I know c1 is going to be greater than 0. Sorry, c1 squared is going to be greater than 0 because the square of a number is always positive. Okay, and I know that v1 dot v1 is going to be greater than 0, right? Because it's a dot product with itself. Okay, so this whole term will be greater than 0. And by the same reasoning, each one of these will be greater than 0. Okay, so this is a sum of positive numbers, so it will be greater than 0. In other words, energy will be greater than 0. Okay, for any non-zero x in Rn. And that's what we wanted to show. Okay, we assume positive eigenvalues, and we showed that the energy has to be positive. Okay, so we've shown that eigenvalue definition implies the energy definition. Okay, now we want to show the other way around. We want to show that the energy definition implies the eigenvalue definition. Okay, so we'll prove that now. It's a bit easier and shorter. Okay, so this is what it looks like. Okay, so we're going to assume that the energy is positive for all non-zero x in Rn. Okay, again, since A is symmetric, we can find v1 through vn orthonormal eigenvectors of A with these corresponding eigenvalues. Okay. Now, since the eigenvectors are in Rn, okay, we can plug in the eigenvector into this inequality, and it will be true. Okay, so we get that vi transpose times A times vi is greater than 0. Okay, now I have A times vi. By the eigenvector relationship, I can replace this with lambda I vi like this. Okay, and now I can rearrange this so that the lambda is on the left. Since it's a scalar, I can move it around. Okay, and then vi transpose times vi is the same as the dot product with itself. Okay, so I have this inequality here, and this inequality here forces the eigenvalue to be positive. Okay, why? Because we know the eigenvector is non-zero. Okay, and whenever you take the dot product of a vector with itself, and it's non-zero, the result is always greater than 0. Okay, so we have lambda. We have a positive number, right, times lambda, and the result is positive. That forces lambda to be positive as well, right? It can't be 0 because then this expression would equal 0, and it can't be negative because then it would be less than 0. So it has to be positive. Okay, so that shows that if we start with positive energy, we're required to have positive eigenvalues for A. Okay, so we've been referring to this term, x transpose times a times x, where x is a variable vector, as the energy of A, which is a term used in physics and engineering. Okay? So the mathematical term for it is the quadratic form of A. Okay? And it's a function from Rn to R, right? Because we have x1 through xn variables, right? And the whole thing sums to a single real number, right? And if you notice, we'll always get degree 2 terms. Okay? We won't get any degree 1 terms. Okay? Okay, so the eigenvalues of A determine a lot about the geometry and the extreme points of the quadratic form of A. Okay? In other words, it determines the shape of the quadratic forms. Okay? So, sort of good case, or the case that's usually wanted by applications, is the positive definite form of A. Okay? So, when A has all positive eigenvalues, then A and its quadratic form are called positive definite. Okay? And what that means, equivalently, is that the quadratic form is going to be positive, with the exception of the origin, x equals 0. Okay. So here's a graph of a quadratic form when n equals 2. Okay, so if n equals 2, our two variables will be x1 and x2. Okay, and then we'll let those variables take on different numbers, and then we'll graph the result on the z-axis like this. Okay, so when it's positive definite, that means for all the x's, it's going to be above the above the positive axis for z. Okay, so it looks like an upward bowl like this, and we get one unique minimum right at the origin. Okay, so negative definite is the reverse of that. Okay, if A has all negative eigenvalues, then A is called negative definite, and the quadratic form is always negative, with the exception of the origin, which will be now a unique maximum, right? And in 2 dimensions, we get this downward bowl shape. If A has both positive and negative eigenvalues, then A and the quadratic form are called indefinite. Okay, and so we get this saddle shape here. Okay, in this case, the quadratic form will take on values like all the negative numbers and all the positive numbers. Okay, and 0 as well. Okay, and the origin will be a saddle point. Okay, that means like it's a minimum if you approach like this, right? And it's a maximum if you approach like this. Okay, that's what a saddle point is. You've probably seen this in calculus, right? So this is the indefinite form. Okay, so these 3 forms don't account for 0 being an eigenvalue, right? When I say positive, I mean strictly positive, greater than 0. Negative, I mean strictly negative, less than 0. Okay. We can get something called a semi-definite form, where if we have positive eigenvalues and 0 as an eigenvalue, okay, then what we call that is positive semi-definite form. Okay, so it's going to be either 0 or greater than 0. So the quadratic form is greater or equal to 0. Okay, but we're going to get infinitely many minimums. Okay, so instead of just the origin being a minimum, we're going to get infinitely many points that are minimums for this quadratic form. Okay, and there's the reverse of that. Right. If A has negative eigenvalues and 0 as an eigenvalue, we get negative semi-definite, and quadratic form is less than or equal to 0, and there are infinitely many maximums. So I didn't have a picture for it, but it's just this flipped upside down. Okay. So I just want to emphasize that, problems of extreme points, minimums and maximums, right? That's usually something left to calculus, right? What you would do for an equation like this to find mins and max would be to use something like the second derivative test, right? And you'd have to do a lot of work, right? What I want to emphasize here is that all that information for quadratic forms like this is embedded in the matrix. Okay? It's embedded in the eigenvalues of the matrix, and whether they're positive, negative, or 0. Okay, so one more thing I want to talk about for positive definite matrices. Okay, so let's consider this A here. Okay, so it's a symmetric matrix, and you can check that its eigenvalues are 9 and 1. And these are the eigenvectors you get if you use the normal method. Okay. And we can normalize those eigenvectors to get these eigenvectors. And so, since A is symmetric, we get an orthogonal diagonalization of A, and it looks like this. Okay. So, how can we use that to apply it to our quadratic forms? Okay, so this is our quadratic form here, right? For A, right? What if we were to sub in A equals Q D Q transpose, our orthogonal factorization here, into A here? Okay? Would it do anything interesting to the quadratic form? Okay, so that's the question. So before we get into that question, we'll talk about change of variables. Okay, so if x is a variable vector, as it is up here, then a change of variables, okay, is an equation of the form x equals py, or y equals p inverse x, where p is invertible and y is our new variable vector in Rn. Okay, so if we want to change variables from x to y, right, what we do is we relate them by an invertible matrix. Okay, and this should be familiar, right? This is how we wrote vectors in terms of some basis, where the basis columns were in P. Okay, and it's the same idea here. Okay, so our new variable y could be considered the b vector of x, where b is the columns of P. Okay, remember we talked about invertible P being a translation between the standard basis and the columns of P, right? And that's what's happening here when we make a change of variables from X to Y. Okay, so I didn't mention all that stuff for no reason. Okay, so remember what we were asking is if we had a quadratic form like this, what would happen if we substituted in our orthogonal diagonalization for A into this? Okay, so here's the answer. Okay, so we start with our quadratic form, and I sub in our diagonalization in for A. Okay, now I'm going to manipulate it a bit, right? I'm going to write it, this X transpose Q part as Q transpose X transpose. Okay. These two things are equal, right? Just by the rule of transpose, right? When you expand a transpose over a product, you transpose both of the factors and you reverse the order. Okay, so it becomes X transpose Q transpose transpose, transposes cancel, and we see that this is true. Okay, so I can write it like this, right? Now we're going to use what we talked about up here. We can interpret Q transpose times X as a change of variables. Okay, so remember, we want P to be an invertible matrix. Q is an orthogonal matrix, so it's invertible. And its inverse is its transpose. Okay, so we're in this situation here, right? Where we have an X and we're changing the coordinates to Y. Okay, and the coordinates are related by this Q matrix. Okay, so I said Y equal to Q transpose X. Okay, so I sub that in here. Okay, and then here I'm just taking the quadratic form of the D matrix, which is the eigenvalue matrix, and if I do that, I just get this. Okay, so what was the point of that? What did that tell us? Okay, it tells us that we can make a change of variables, okay, from X to Y using Q as the matrix connecting them, okay, and it turns this quadratic form into this quadratic form. And we notice now we have no cross products in it. Okay, so we've eliminated any terms that have, you know, more than one variable in them. We only have squares here because we took the quadratic form of a diagonal matrix. That's why we get this. Okay, so this just summarizes what we did. Okay. If we change from variables X to Y, and we relate the variables by the invertible Q, okay, the result is the quadratic form of a diagonal D with no cross product term. Okay, so we started with this. We did this change of variables using this equation, okay, and then we got a quadratic form in a different set of variables, okay, that has no cross product term in it. Okay. And the terminology for this is that the columns of Q, which are the orthonormal eigenvectors of A, are the principal axes of the quadratic form. Okay, and the principal axes theorem just states that this is always possible, right? It's not just this example. Whenever you have a quadratic form in a variable X, you can always transform it into a quadratic form without any cross product terms, okay? Just by doing a change of variables, x to y, where they're connected by the q that comes from the orthogonal diagonalization of A, since A is symmetric. Okay, so that's the lesson of this part. This is always possible.